Okay, let's do assignment 2, or unit 3 on vectors. We're going to do the vector conversion worksheet. Okay, now let's talk about position vectors on an XY plane. What we're going to do today will apply to all vectors, whether it's velocity, acceleration, force, all kinds of different things. But we're going to start off by just talking about position vectors. So this is my x-axis in meters. This is my y-axis in meters. So, and let's say my object is located over here somewhere. What we need is a way of expressing where that object is on the XY plane. Where is it? Where is it located with respect to the origin? We have a word for that. What do we call where something is compared to the origin? Well, we call that position. So what is the position of this object? Well, there's two ways of expressing that. First of all, I can express it with a distance and an angle. Like, how far away is it from the origin? What distance is it away from the origin? Okay, I'm going to call that R. And then it's going to have an angle. And we need to have a reference for where we're going to measure our angles from. We're going to measure the angles from the positive x-axis, always. And we're going to rotate. If I rotate counterclockwise, I'm going to call that a positive angle. If I rotate clockwise like this, I'm going to call it a negative angle. But in any case, the angle will always be measured from the positive x-axis. So there are two ways of expressing this. Where this object is with respect to the origin. I can use what are called polar coordinates. Or I can use what are called rectangular coordinates. And what we want to do is define what these are, and then I want to be able to go back and forth between them. I want to be able to convert from polar to rectangular and rectangular to polar coordinates, and that's what we're going to do today. Polar coordinates, here I have vector r, that is position vector r. That's position vector r. In polar coordinates, I'm going to say r is a distance away from the origin, or a magnitude, how far away it is, and in what direction is it. R and theta. Now, this, if I give you an R and a theta, I've given you the polar coordinate for the position, the polar coordinates. Now, notice though that I can also tell you where is this object along the x-axis, and where is this object along the y-axis? So r sub x and r sub y. Now if you express the position of this object using how far along you are in the x direction and how far up or down you are in the y direction, these are rectangular coordinates. And by the way, this is called the x component of vector r, and this is called the y component. We have two component vectors. We've broken the one vector up into two other vectors, the x component and the y component. So I would say vector r here is equal to r sub x and r sub y. Now what we want to do is what if I give you the x components and I want to calculate what the polar coordinates are. Well, I use just what we did in the last assignment. If I give you Rx and Ry, and I want to express R and theta, I would use this. R equals the square root of Rx squared plus Ry squared. That is, I just used Pythagorean theorem. Now, if I want to calculate the angle theta, well, I know Ry and Rx. I know the ratio of y over x is tangent, so what I can do to get the angle is use inverse tangent. Ry over Rx to get the angle. Now, I'm going to add something to this, and I'm going to show you why we're going to add it here in a minute, but I'm going to add plus 180 degrees if Rx is negative. If it turns out that if your x component of your vector is negative, when you use inverse tangent, you have to add 180 degrees to the answer your calculator gives you. And I'm going to show you why in a few minutes. Now, to use for rectangular coordinates, it's pretty easy. If you're given r and theta and you want to find Rx, you just say Rx is equal to r cosine theta, and Ry is equal to r sine theta. So, and there's no tricks or anything to worry about here. You just plug in the angle that's given, times cosine, or you operate cosine on the angle and multiply it by r, and you've got r sub x. R sub y is, the r times sine theta. Yes? Oh, whoops. Thank you. So this is what you need to go from rectangular to polar. This is what you need to go from polar to rectangular. And what I'm going to show you in the next video is why do we have to add 180 degrees if r sub x is negative. I want to show you now why we have to add 180 degrees to our answer for inverse tangent if your x component is negative. And it's pretty easy to understand, actually. So let me show you an xy plane. So here's y, and here's x. Now let's say a position, it looks like this. 1, 2, 3, 4, and 1, 2, 3. Let's say the object was up here. And so I've given you the position vector of this object in rectangular coordinates, haven't I? That is, vector r is equal to 4 meters in the x direction and 3 meters in the y direction. Well, what if I want to express vector r in terms of polar coordinates? Well, the magnitude is easy. R is equal to the square root of 4 meters squared, that is the x component squared, plus the y component squared. And of course, all physics teachers and math teachers like to use 3 and 4 because what do you get? You get 5, right? Because what's 4 squared? 16 plus 3 squared, 9. 16 plus 9 is 25. Square root of 25 is 5 meters. And we can calculate the angle. Theta equals the inverse tangent of the y value, which is 3 meters, over the x value, which is 4 meters. And when you plug that into your calculator, you get, well, let's see, what do we get? Oh, where's my calculator? Let's see, I'm going to say inverse tangent, oops, wrong one, inverse tangent of 3 divided by 4. I hit enter, and I get 36.9 degrees. Okay? So follow along, put that in your calculator, make sure that's what you get. But what if I was down here in the, now remember, this is called the first quadrant, and then over here is the second quadrant, this is the third, and this is the fourth quadrant. What if my object was in the fourth quadrant? So -1, -2, -3. What if it was down here instead? Well, I think you can see that even now your x quantity is still positive, but your y quantity is negative. But what happens when you use Pythagorean theorem? What is -3 times -3? It's still positive 9. Negative times a negative is a positive. And so you still have 16 plus 9. You still have the square root of 25, which is still 5 meters. So this is still 5 meters long, like it was up here. But now let's use inverse tangent. And if you say, okay, well, y is -3 meters, and x is positive 4 meters, and when you plug that into your calculator, you're going to get -36.9 degrees. Now that makes sense, doesn't it? Because look, this rotates positive, and we said that, or counterclockwise, we said if we rotate from the x-axis like this, it's a positive angle, but if we rotate down like this, it's a negative angle. And your calculator knows that. The algorithm in your calculator knows that. So it gives you this angle. What if you wanted to express it as a positive angle? What would you have to do? Well, you could express it like this, like that. You could add 360 degrees to this. You can go -36.9 and then add 360 degrees, and you'll get, a positive angle. But this is good. You can use this -36.9 degrees. It's good enough. Now, let's go to the second quadrant over here. -1, -2, -3, -4. And if I come up here, there's my position. And x is -4, but it gets squared. So -4 squared is 16, plus 3 squared is 9. You get 25 squared root of 25 is still 5. So it's still 5 meters. But let's use inverse tangent. And really pay attention to this part. This is the part we're really trying to emphasize here. The inverse tangent of the y value, which is 3 meters over -4 meters. Notice that our x value is negative now. When you do that, you get -36.9 degrees. But that's the wrong answer. That's not where that object is. It's 5 meters away, but not at -36. Where is it? I'd go -36.9 degrees, but where is it compared to this? Compared to this, it is in the opposite direction, which is 180 degrees away. So what you need to do to get to this angle right here is add 180 degrees to your answer. So theta is -36.9 plus 180 degrees. It's 143 degrees. 143.1 degrees from the positive x-axis. And this is your angle. Your now look, take a look at this. Why did this happen? Here we have 3 divided by negative 4. But over here, we have negative 3 divided by 4. It's the same answer. 3 divided by negative 4 is negative 0.75. This is negative 0.75 down here. Your calculator is not smart enough to know the difference between the 4th quadrant and the 2nd quadrant. You have to be smarter than your calculator. Let's take a look at the 4th quadrant. Well, if you're down here, you're still 5 meters away from the origin. But what angle? What angle is this? Well, you're going to have the inverse tangent of negative 3 meters over negative 4 meters. Well, what's negative 3 divided by negative 4? It's negative 0.7, positive 0.75. A negative divided by a negative is a positive. And your calculator is going to think you're in the 1st quadrant. So when you plug this in your calculator, you get 36.9 degrees. But that's not where you are. Here's 36.9 degrees up here. What do I have to add to it to get to where I really am? 180. So look, in both, on the left side, quadrant 2 and 3, your x component is negative. And on both of these, I had to add 180 degrees to get to the right angle, or the correct angle. So, that's why we say this. To find the angle using inverse tangent, it's the y component divided by the x component. And then you look at your x component. If it's negative, you add 180 degrees if negative rx. So that's what you have to know in order to convert from rectangular to polar coordinates. If you want that angle, if I give you the y and the x, you have to use, if the x is negative, you have to add 180 degrees to your answer.